Hey guys, this tutorial is gonna be awesome because we take the new closures feature and we use it for some actual practical stuff. So this is sort of what we're gonna create. It's not too crazy, very simple animation system, but with the power of closure, we can provide a node group that handles the animation, and we can allow the user of that node group to plug in their own easing curves. In this case, you're just gonna have to watch and see. There's a lot of stuff I want to show you. If you don't know what a closure is, I have a video here on the channel. It's like a first more theoretical look. But if you've never heard the term closure and also not in combination with Blender, then maybe you should check that video out. So let's jump into a new file and start from scratch. Okay, so I am still in Blender 5 Alpha, just like in my first closures video. Let's go to geometry nodes. Now I'm sort of gonna reinvent the wheel here a little bit because of course you can do animations with keyframes and with easing curves and with modifiers on those curves and all that kind of stuff. But we want to create our own little motion system in geometry nodes. So of course we needed geometry nodes, a node tree, and a very simple animation would be a bounce. So the cube should start at the top and then fall down and bounce a little. How would we do that? Very simple. We just plug in a transform geometry so we can move the Z axis. Now, of course, we need to get in the time. So shift a time, which gives us the frame. Now we want to be able to have the animation between a start and an end frame that we want to plug in from the outside maybe. Right away, we can do a map range. And we can plug the frame into the value. Okay, so let's start maybe at frame 10, and we want the animation to go from between 10 and 40. And this gives us now a factor between 0 and 1, which is always good to have, because, for example, we can plug that into a float curve, and we can use that as a factor of a mix node for a vector. So between two vectors, our start and our end vector. So let's say the end vector should be 1, and then the start should be 5 on the C, and this is the factor we use, and we plug that into the translation, and we already have something. So our animation should start at frame 10, yep, okay, and it should end at frame 40, where it is now on the ground plane, basically. How can we make this look a little bit more interesting? Well, we can zoom in on our float curve and create sort of a bounce. So over here on the left side of this float curve would be our factor 0. Over here would be 1. Or in our case, it would start from a frame 10. So this would be at frame 10 and this would be at frame 40. And because we have clamp switched on, all the frames before 10 will still be 0. And all the frames after 40 will still be 1. So think of this x-axis here as our time, and then the y-axis is just a factor between a 0 and 1, which is our mix factor between those two vectors. So if we want to bounce, we have to sort of bounce this way. And with those handle types down here, we can make it bouncy. So let's go here, then we add our first bounce, something like that. So maybe we accelerate, bounce, and then we have a big bounce. Let's just do 2 bounces. And then we probably have another smaller bounce like this. This one needs to be sharp. This one needs to be round. This one sharp. I think this would be a bounce. Now let's see what it looks like. Go shift left cursor. And our animation, let's just make it 50, okay? So this is the animation down here. So between frame 10 and 40, we should have a bouncing. Yep, of course now it's sort of upside down, but that's because we have to go from the bottom left to the top right in our curve. Yeah, so we have a bounce twice animation. Yeah, so this is very simple, and if we want to provide this as an animation system now, we would take all of this, put it into a group, and then on the group input, of course, we would provide like the from and the to, but of course we need to call this like start frame, end frame, so that the user of this node group knows what these values are. And Whoops, this was the wrong one. End frame goes in here. Okay, that gives us the factor. Then we have the curve. And of course, we want to also be able to have the start and end vector on the outside for the user. And then we have this. Yeah, okay, so this is cool. If we get out of this node group, we can now have a single node group, which would be our animation system. And for the end frame, we wanted 40. So let's see if it still works. Yep. Of course, we can now bounce maybe from left to right or from any vector to any other vector. But as you can already see, there's a bit of a problem. This is not an animation. This is a bounce. Because inside here, we configured this float curve, which is always a bounce. And there's no way for me to plug in a float curve. So wouldn't it be nice if I could copy this, paste it out here and go, hey, you animation, between frames 10 and 40, I want to animate from this vector to this vector with this curve, and I want to plug you in somehow. And that is exactly what the closure is for. So let's put this curve into a closure, which is in utilities, closure, which gives us this closure zone, sort of like a node group, but the output of this node group is a closure, which is a function. So the input would be our value. Okay, and the output would be our value. Very simple closure. And instead of using a float curve in here, we take that out. We plug in our evaluate closure node. The simplest way is just to shift a utilities, a closure evaluate, put that in here. And then we plug that in there. And then I remove it. And on the outside, now I have a closure socket. So I can plug my function into this generic animation system. And in here, I just drag this out. I evaluate this closure. As you can see, the closure, the function, needs a value input, which is this, and it has a value output, which is this. So we replaced this static, fixed, hard-coded float curve with a flexible closure. And the user of our animation system can now plug in their own function, their own easing curve. Now let's go back in here because there is one thing in here that I saw. By plugging in this evaluate closure, we get this error here because it says the node input does not support fields. So the evaluate closure, a closure is always evaluated like a field. You know how we have the fields in geometry nodes where you, for example, you say, okay, I want to transform the position of each vertex by maybe a random value. And the set position node goes through each vertex and then applies that transformation based on the position. The position would be the field. There's other fields like the point size and the normals and all of that. So the evaluate closure doesn't give us just a single value for the entire geometry. It gives us a value for each point of our geometry. And that is why we get this here. So the transform geometry node cannot handle the fact that this output here from the closure is actually a value for each of the vertices of our cube. So instead of transform geometry, we're going to have to do something else. We're going to have to do a set position, which, like it just said, is able to handle a field because it can set the position of each vertex. And we simply plug this into the offset. So we get the same thing, bouncing. Okay, so I think we already have a cool animation system. We can plug the start and the end frame. We can plug the start and the end vector, and we can plug in our own custom closure for the easing. If your animation system can't only handle transformation, maybe it can also do rotation and stuff. Maybe you would have a translate closure and then a rotation closure and a size closure. And, you know, for this tutorial, I'm going to keep it simple. This is my animation system, very simple node, and we can plug this in. So, of course, we can take this, we can group it. This group output gives us a closure, Now this group would be a bounce 2 times, right? And if we wanted to create a bounce 3 times, we could just go in here. We could copy this, maybe go out here, create a new utilities closure, paste that in here. We take the value input, value output, because that's what our animation system expects. And then we play with this and make it bounce 3 times. Maybe like that. Then one more, like so. Of course, this one needs to be sharp, like that. And then the last one should be just very short, like this. Okay. Now, if we plug this closure in here, our cube should bounce 3 times. Perfect. So we have another group. Take that, group it, go out, and call that bounce 3 times. Bounce 3 times. Perfect. And that is the amazing power of the closure, because the closure is a data type for a function, and you can define the function, and you can give it to some other complex node group that does something with your function at a certain point in that workflow. Okay? Now this is cool and all, but this is still extremely simple. We're just using a float curve. Who says that we have to interpolate using a float curve? We could create a closure that does something completely different. For example, what if we shift a curve, a Bezier curve? Now let me go in here and scale this up a little bit so you know these curves. This is the default curve that has this little bend in it on the y-axis. This curve also has a pretty low resolution, so let's turn that up to make it nice and smooth. Now what about we go in here and we create a closure again, so utility, closure, closure, that uses this curve. Okay, I'm gonna pin this. So we're just gonna need the curve in here, and there's a node in Geometry Nodes that lets you sample the curve along its path, and it is called the sample curve node, which just gives us at a certain position, again, a factor between 0 and 1. So that will be this guy. Of course, now it's called factor because I plugged it in. And remember, the names have to match. The closure, our animation system, expects a closure that has the input name called value. And it also has, it expects an output name called value. Now, of course, this is not the value that I want to output here from my closure. I actually want to make the cube move according to the y value of the position that I'm evaluating here. So I want to evaluate a vector. The vector I want is the position, which gives me a vector which I can separate. And like I said, this would be the y-axis, and I want these distances here. So if we look at it from the top, we would be evaluating along this curve at the different points given by our input factor. And then I want to use this distance here for the output of my closure, which would be the y value. Okay, let's see what this does. Maybe we have to add some factors and stuff. So let's go to frame 1. We're using this closure now, and shift left. It's not working. You know what? Instead of this, let's just use this position. So let's go back to frame 1. What's happening? Okay, yeah, so it's moving. So we're moving from the start vector towards our target vector. And then we actually go back to our start vector. And that is why the motion is now this. Okay, so we're moving down and back up. You can see the back up, it's going very slow. Down is faster. That's because the curve looks like this. Okay, cool. Now, of course, the curve, the y value coming out of here is not between 0 and 1, but that's what our animation system expects. Or does it? Because here we have clamp factor. So it just clamps it between the one vector, the start vector and the end vector, but we can also switch that off actually, and then we can sort of overshoot even. So let's see, how can I edit this while looking at it? Okay, so let's go back to frame 1, hit play, and now while this is playing, I'm gonna play with my curve. Okay, now I even made it 3-dimensional now, but we're only using the Y value. Okay, so we could scale on the C to 0. So we're only using this Y, and then we could probably, when we look at this from the top, we could probably overshoot this way too. A little bit. Scale it in, maybe rotate it. So what does that look like? See, when we go back up, we actually overshoot a little. Whew! And that is that little curve dip down here. So we can use a Bezier curve in the viewport for our animation. And that is the power of the closure. We can use anything that gives us the factor for the animation between the first and the second vector. I think this is just so cool. Now, this is an extremely simple example, but I'm sure you can already think of many cool things that people might come up with, and then they provide you with a little node group that does something amazing, and they allow you to plug in your own closures, your own functions. Now, to clean this up, of course, I would also put this into a node group, and I would plug the Bezier curve in here. And what else? Oh yeah, okay, let's make this really cool. So we have this now. Let's just call it curve. And another thing we could do here is, who says that we just want to read the Y value of our curve? Maybe the user has a curve that is going up on the C axis. And there's a cool thing we can do. So we can plug in a switch, what is it called? Menu switch. That is a really cool node. Plug that in here. And then on the menu switch, we just remove A and B and we plug in X. Whoops, this is set to geometry. Of course, we want float. So X, Y, and C. We use that. And then we use this on our group input. And if we go out here, you can now see we can define which axis we want to read. So this is bouncing using the Y. And if I set this to X now, it just goes straight down because the X is basically just going along the curve on the X, which is laying perfectly flat. So we already have another cool closure for our easing curve. Now let's go back to a bounce twice. Put these out of the way because there is another thing I want to show you. And that has to do with the fact that inside of our animation here, remember before I said that we have to use the set position node because the evaluate closure is like a field, so it evaluates the function that we provide for each vertex. So think about that. That means our closure has access to the actual fields, right? So like the position of each vertex. So let's see what we can do with that. For that, I'm gonna create a Shift A mesh. Let's just do a donut, maybe. Go into edit mode and rotate it so that it's standing up like this when we look at it from the front. Let's go back out here. On the donut, which does not have any animation, I'm just going to hide the cube for now. The donut also gets a geometry node, and it has to use this geometry nodes node tree. Of course, it could have its own using the same group. Let's just use the same one. So for now, we just have the simple bounce that we had before. But since we can access every single vertex inside of our closure, we can do stuff like maybe, stretch it while it's bouncing or stuff like this. So let's try that. The blend file of this tutorial is available at patreon.com/chrisp. Okay, so let's go in here. Let's take the float, or let's just take all of this, copy it. And then down here, we paste it and we plug that in. So now we have our bounce. And I want to modify this bounce so that every vertex moves differently. Right now, all the vertices move just as one block. But like I said, the closure is evaluated like a field, so we have access to the fields of the vertices. For example, the position, which is exactly what we need. So let's figure this out real quick. Let's say we have, let's go back to the end here. So this is the final position. Now, if I want to stretch this donut this way while it's, accelerating downwards, I would have to figure out sort of the distance from here to the vertex. So this vertex would be further away from the bottom than this vertex. So I'm gonna need the field, the position. And remember, this is not the position of the donut, this is the position for a single vertex now. And I can separate X, Y, Z, because I'm only interested in the C value anyway. And then I can use a cool node, which is the attribute statistics. I can plug in the C value, which is this bottom one here, from my input geometry. Okay, so I have to use the input geometry, which is that one up there, coming from the donut. Okay, and that gives me now the minimum of the C positions of all of the vertices, and the maximum and the range. And we can use that to determine how far away is the vertex from the bottom. How do we do that? Simple map range node should be good. And we do the float. The value would be, okay, so we need, we copy this again. We take this for the value. This will be the C position of the vertex. And then from min would be, well, the minimum C position of all of the vertices of our donut is this. The maximum C position of all of the vertices of our donut is this. And then we map it to be between 0 and 1. So let's see what that gives us. Plug in a viewer node. Of course, we need the geometry. And that gives us this gradient from a black to white. Okay, I think I want this to be the other way around, because when I think about this, switch this off, while this is falling down, I want the ones on the bottom to be affected more, pulled down more than the ones on the top. Yeah, so let's switch this around from 1 to 0. So now it's a black at the top. So this is a nice factor now that we can use to modify our float curve. So what if we plug that in here? Then we get this. Oh, of course we have the value. Well, we kind of need to plug the value in with this. So how about we take another float curve like that. We use this as the factor for that float curve, and this would be our closure value. And then we should have this is that. And if we bring this up a little, then we have a little bit of a bouncy, stretchy thing, sort of like a cartoony animation. And we're still working with the same animation system that we had before, except that we now have a different closure that does something on each vertex. And this is just mind-blowing that this is possible. I think this is just so awesome that the closures are evaluated for each vertex and we can do stuff like this. Now, of course, you might be thinking, okay, now I have this float curve in here, which is the same as the float curve that bounced twice. I don't want this to be fixed like that. Can't I just plug in my original float curve? Well, of course you can. How about we plug and evaluate? Let's take this one. We evaluate that one. This is the value in, this is the value out. So let's use the same bounce twice. Okay. And if we want to make it bounce 3 times, we just take this closure. And it's still bouncy and elastic. So we could take all of this, right? All of this, put that into a group. This would be the node group that makes it elastic. So really what we need is the combination of a bounce. Let's take the bounce 3 times. Then we make it elastic. And that's our animation. If we hit play. Cool. So if we don't want the bounce, we could plug in the Bezier. You remember that's the one that we drew on in the 3D viewport that does the down and then back up with a little overshoot. Or we can bounce 3 times. Let's bounce 3 times. Dip, dip, dip. This is so cool. Now we have all of these node groups here. We have the bounce twice, bounce 3 times, the elastic, the one that takes the curve. We have the animation node group. Now all of this could be packaged together nicely and provided for other users to use as a geometry nodes based animation system. In this case, it's just moving something from A to B, and the user of that animation system can use the predefined nodes like these here, or create their own closure. I hope this tutorial gives you a practical example of the amazing power of closures. Now this is just in geometry nodes, but I mean, if somebody from the Blender development team is watching, the concept of a closure, of being able to define something, plug it into something else that executes your defined thing, that would also be amazing in shader nodes. I don't know if that's even possible. If the GPU, for example, could handle this, I have no idea. And of course, also in the compositor. So thank you for watching, liking and subscribing. If you enjoyed this video, consider watching another one. Say hi in the comment section. See ya.